After studying this module, you will be able to learn the significance of Ninhydrin method of fingerprint detection, the chemical and physical parameters involved when Ninhydrin is being used as a fingerprint reagent, the post-treatment and the pre-treatment procedures which enhance the quality of Ninhydrin developed fingerprints, and lastly an assessment of Ninhydrin analogues vis-a-vis the parent compound as a fingerprint reagent. Introduction. A latent fingerprint is formed when the sweat pores of papillary ridges leave a deposition of perspiration on a surface with which the finger has been brought into contact. Human skin possesses three types of sweat glands: the acrine glands, the apocyrin glands and the sebaceous glands, the secretions of which contribute to the fingerprint deposit. Acrine glands are widely distributed throughout the body and are particularly numerous on the palms of hands and the soles of feet. Besides the water content, acrine sweat contains up till 1% of other substances, of which about one-half are inorganic ions. The remaining half consists of organic derivatives like urea, sugar, lactic acid, amino acids, proteins and fatty acids. The amino acid content of sweat residue may be fixed by treating the latent fingerprint with a solution of Ninhydrin reagent. The amino acid Ninhydrin reaction produces a purple colored compound called Ruhmann's purple, which becomes deposited along the ridges, making the latent fingerprints visible. Ninhydrin is particularly useful for developing fingerprints on porous and absorbent surfaces like paper, paper products, cardboard and wood. Whereas the inorganic ions and most of the organic ingredients of sweat, they tend to interact with the cellulose content of paper or wood, the amino acids remain intact. They are in fact inert. Moreover, with the passage of time, the amino acids do not migrate within the capillaries of the substrate. Therefore, the Ninhydrin method makes it possible to develop fingerprints that are many years old. We next take up the preparation and properties of Ninhydrin. Ninhydrin was first synthesized by Ruhmann in 1910 in an attempt to oxidize 1-hydrindone to 1,2-diketohydrodine. However, a di-substituted hydrindone was obtained, which was subsequently hydrolyzed to Ninhydrin. Ninhydrin crystallizes as pale yellow crystals from the ethanol solution. On heating in the solid state, it changes to pink or red in color at 125 to 130 degrees centigrade, becomes deep purple at 130 to 140 degrees centigrade and finally melts with decomposition at 241 degrees Celsius. When exposed to sunlight, Ninhydrin turns red. For this reason, it is always stored in a cool and dark place. Normally, organic compounds having two hydroxyl groups on the same carbon atom are unstable. However, Ninhydrin is stable. It owes its stability to intramolecular hydrogen bonding. When heated in vacuum or when treated with thionyl chloride, Ninhydrin dehydrates to 1,2,3-indane trione. Compounds such as 1,2,3-indane trione, which have got a vicinal triketonic functional group, are also useful developing reagents like Ninhydrin. However, the quality of the developed prints are not as good as with Ninhydrin. The most useful reaction of Ninhydrin is with amino acids. A purple colored compound is formed which as a result of this reaction. The product has come to be known as Ruhmann's purple, or in short RP. The amino acid Ninhydrin reaction has proved to be useful in several analytical procedures. Incidentally, this very reaction makes Ninhydrin a reagent for fingerprint development. Now we take up Ninhydrin as a fingerprint reagent. Ninhydrin was first used as a fingerprint reagent in 1954 when two Swedish scientists, Odén and Hofsten, developed latent fingerprints on paper, cardboard and similar materials with the aid of Ninhydrin. A year later, Odén patented this procedure. Broadly, the procedure for developing latent fingerprints involves spraying the Ninhydrin solution on the surface containing the latent impression from a distance of about 6 inches. After the solvent evaporates, the solution is resprayed. The surface is then heated for a short time while allowing it to come into contact with the heat source. If quick development is not required, the item may be allowed to dry at room temperature. Better results are obtained by natural drying. During experimentation, there are several parameters that need to be adjusted for adequate and satisfactory development of latent fingerprints. These are the chemical parameters such as concentration of Ninhydrin solution, the nature of solvent and the acidity of the formulation, as well as physical parameters such as mode of application, heating temperature and relative humidity. First we take the chemical parameters. Concentration of Ninhydrin varying from 0.2 to 1.5% have been found to be suitable for fingerprint development. Various types of solvents have been tried out for preparing Ninhydrin solution. The reagent dissolves in most organic solvents such as methanol, ethanol, acetone, diethyl ether and naphtha. The choice of the solvent depends in part on whether the document is scripted or not. Most organic solvents tend to despoil the calligraphic script. Freon 113, also called fluoresol, proved to be the most remarkable solvent for dissolving Ninhydrin. It does not interact with ink. It is absolutely non-toxic and therefore there is no chance of the surface becoming degraded. Because it is non-toxic, it also poses no occupational hazard to the user. Above all, it is non-inflammable and therefore quite safe to use in a laboratory. As a result of this, characteristics of Ninhydrin based composition has come to be referred to as non-inflammable Ninhydrin or NFN. The NFN develops fingerprints on a wide range of paper items. It provides a minimal amount of background effect. Moreover, it is effective on surface coated papers such as currency notes as well as gummed side of postal stamps. It is however being feared that it may not be possible to continue with NFN in the years to come. Freon 113 belongs to a class of compounds called chlorofluorocarbons. These compounds are being banned out under the terms of the Montreal Protocol on phasing out of the ozone depleting substances. There is therefore a need for a suitable replacement of Freon 113. Petroleum ether provides an alternative as it too does not react with ink. However, petroleum ether is highly inflammable and explosive in nature and is therefore considered hazardous. Supercritical carbon dioxide is being considered as a possible substitute of Freon 113. We now take up the physical parameters. Ninhydrin is applied to the surface impinged with latent fingerprint generally by spraying, swabbing or dipping. Of these, dipping procedure is most extensively used. However, fragile papers such as paper napkins tear apart on dipping, and therefore spraying procedure seems to be better for this type of surface. Swabbing action tends to smear ink and is therefore avoided as far as possible. Less conventional methods include exposure to ninhydrin fumes, dusting with ninhydrin powder, or placing a paper dipped in ninhydrin solution over the finger impression. If development time is not a constraint, ninhydrin sprayed documents should be allowed to develop at room temperature. This may take a few days, but the results are excellent. Normally, however, the surface is heated to 80 degrees Celsius so as to accelerate the development process. The mode of heating is also important. Heating may be carried out by a steam iron. Better results are obtained if the iron is moved 1 to 2 centimeters above the surface. Most forensic science laboratories have adopted this procedure. Others have shifted to microwave ovens for heating and steaming. In the absence of these equipment, the object may be waved over a flask containing boiling water. In other cases, heating has to be carried out in a humid atmosphere. Optimum development of fingerprint occurs at a relative humidity of 65 to 80%. Modern fingerprint laboratories are endowed with ninhydrin acceleration chambers. There is a provision to control temperature as well as to maximize the humidity in such chambers. Paradoxically, the developed prints are kept in humid atmosphere, then they fade out. Light and heat are other factors that cause fading out of the imprints. When ninhydrin developed prints are made fluorescent by post-treatment with zinc chloride, which we will be discussing in the next section, they fade out on exposure to sunlight or xenon arc light. In presence of moisture or high humidity, the fluorescent character is lost, and so is the clarity of the prints. To extend their lifetimes, it is recommended that ninhydrin developed fingerprints should be stored in a dark place at a low level of humidity. Next, we take up the post-treatment of fingerprint developed by ninhydrin. Although the ninhydrin method is considered to be a standard procedure for developing latent fingerprints, it suffers from a number of drawbacks. The chemical reaction between ninhydrin and the amino acid content of sweat deposit is quite slow, and therefore the developing time is quite long. Many surfaces interact with ninhydrin, giving a strong background and coloration that makes the developed fingerprints less sharp. Further, the concentration of amino acids in perspiration is quite low, and hence the developed fingerprints do not show a sharp contrast. Moreover, the method is not applicable to non-absorbent and dark surfaces. Lastly, on many items, the ninhydrin developed prints tend to fade out at a very short span of time. In order to avoid these problems and to improve the working performance of ninhydrin reagent, the procedure for fingerprint development may be modified. The modifications involve the conversion of non-fluorescent Ruhmann's purple deposited along the ridges into a fluorescent derivative by post-treatment of developed prints with a suitable metal salt. The fluorescent deposition shows a marked enhancement and clarity and as well as sharpness when illuminated by a light source. Post-treatment with metal salts in concert with arc lamps. Ruhmann purple, the reaction product of ninhydrin with amino acids, forms coordination compounds with many metals. The metal Ruhmann purple complex are generally red or orange in color. Some of these are fluorescent in nature. The reaction may be used to overcome the contrast problem of ninhydrin developed prints as well as to improve the stability of fingerprints. The reaction of Riemann purple with the salts of group 12 metal like the halides or nitrates of zinc, cadmium or mercury in ethanol or fluorescein 1,1,3 solvent mixture produces a photoluminescent complex. However, invariably zinc ions is the reagent of choice for post-treatment methods. After the solvent evaporates, the sample is dipped in liquid nitrogen so as to bring down the temperature to about -200 degrees centigrade. When illuminated with under an arc lamp, intense fluorescence is produced. A xenon lamp is the most suitable choice for illuminating the plinths developed by Ninhydrin and then post-treated with zinc chloride. A Watkins lamp is also suitable for this purpose. The procedure offers several advantages. The post-treatment may be carried out only when it is deemed necessary. If a sufficient degree of clarity or contrast is produced with Ninhydrin alone, the subsequent steps may be completely avoided. No expensive equipment like a laser is required. Further, prints may be photographed under conventional conditions. Post-treatment with metal salts in concert with lasers. The arc lamp induced fluorescence is no doubt cost-effective method for developing latent fingerprints, but it suffers from a few demerits. The fact that post-treatment has to be carried out at -200 degrees centigrade rules out the examination of larger exhibits removed from the scene of crime. It is difficult and impractical to store cryogenic nitrogen in big tanks. The problem may be obviated by substituting the conventional arc lamp by sophisticated laser equipment. With lasers, there is no need to take the sample to liquid nitrogen temperature except in cases which require special handling. Moreover, the rich deposit produces a stronger fluorescence with lasers than with arc lamps. Laser excitation enables detection of very old prints after these have been developed with Ninhydrin and post-treated with zinc chloride. Fingerprints developed by Ninhydrin zinc chloride method become highly fluorescent under argon laser. At 480 nm, the argon laser produces appropriate excitation for the prints to become fluorescent. Further, with zinc chloride post-treatment and argon laser examination, the laser method may be extended for detection of fingerprints even on non-porous surfaces like glass, plastic and metal. The complexes formed by the combination of Riemann purple with europium-3 or terbium-3 salts too have been found to be suitable for fingerprint development, particularly if the background surface of the evidence is fluorescent in nature. These complexes show enhancement of lanthanide luminescence via intramolecular energy transfer. Moreover, the lifetime of the luminescence is much longer than that of usual background fluorescence. The lanthanide complexes are therefore suitable for time-resolved luminescence imaging. There are a few disadvantages associated with lasers. The casework has to be carried out at the Fingerprint Bureau. Portable lasers which may be carried to the scene of crime are not yet available. Laser equipment is quite costly. When optical spectroscopic techniques are used in combination with lasers, the operational procedures become tedious and complex. However, the end results obtained with lasers are so remarkable that one becomes inclined to believe that their merits outweigh the demerits. Next, we take up the pre-treatment of developed prints. The amino acid content of sweat deposition is quite small and therefore rich details are often not visualized clearly even after post-treatment with zinc chloride and laser examination. To improve the sharpness of developed prints, pre-treatment with hydrolytic enzymes, for example trypsin, may be tried. These enzymes hydrolyze the protein content of perspiration to amino acids, thereby increasing the chances of enhancement of developed fingerprints. Initial attempts to pre-treat the fingerprint samples proved futile because the enzymes were dissolved in non-aqueous solvents in which they denatured. Subsequently, however, the dusting of powdered enzymes before the Ninhydrin treatment was tried. This gave pronounced enhancement of latent fingerprints, especially those that were 2 weeks or 3 months old. The methodology involves the following steps. The enzyme is applied by dusting over the finger mark and the sample is incubated for about 40 minutes at 35 to 40 degrees centigrade under a relative humidity of 80 to 90%. The article is then dried and excess enzyme is blown off. This is necessary since the enzymes too react with ninhydrin, giving colored compounds. The dried enzyme-free sample is then treated with ninhydrin and re-incubated for about 18 hours. If rich details are still not clear, then further treatment with zinc chloride followed by laser examination may be carried out. Enzyme pre-treatment method cannot be applied to routine samples. It requires a long developing time. It is unsuitable for field work. The technique may be tried out over articles bearing extremely weak fingerprints. Ninhydrin analogues. Till the early 1980s, it was endeavored to improve the ninhydrin method by altering the solvents, the composition, or the pre-treatment and post-treatment methodologies. Later, a different approach was adopted. Several derivatives of ninhydrin were synthesized and tried out for developing latent fingerprints. It was anticipated that the derivatives of ninhydrin possessing diketonic functions would react with amino acid content of sweat the same way as ninhydrin does. With several ninhydrin analogues, this expectation came out to be true. The most promising ninhydrin derivative is benzo-F-ninhydrin. This reagent develops green colored fingerprints with excellent resolution. Improved sharpness was observed on treatment with benzo-ninhydrin developed prints with zinc chloride followed by examination under an argon laser. However, still better results were obtained with frequency doubled neodymium ytterbium aluminium garnet, which is abbreviated as NDYAG laser. The emission wavelength of this laser device, which is 532 nm, closely matches with the absorbent band of benzo-F-ninhydrin amino acid zinc chloride complex. An isomer of benzo-F-ninhydrin, which is benzo-E-ninhydrin, gives good quality pink colored fingerprints. Another ninhydrin derivative which develops latent fingerprints with appreciable degree of sensitivity is 5-methoxy-ninhydrin. On paper, this reagent produces fingerprints as efficiently as ninhydrin. Yet, fluorescence after zinc chloride treatment is considerably stronger than with ninhydrin developed prints, particularly when these are examined under a copper vapor laser. 5-methoxy-ninhydrin has also proved useful for developing fingerprints on currency notes. Benzo-F-ninhydrin and 5-methoxy-ninhydrin offer operational advantages over ninhydrin. Prints developed with either of these reagents showed stronger room temperature luminescence after zinc chloride or cadmium chloride treatment in comparison with similar prints developed with ninhydrin alone. These were also effective in lifting fingerprints on cardboard where the background luminescence precludes the successful development of fingerprints with ninhydrin alone. Summary: Ninhydrin is the most suitable reagent for retrieving latent fingerprints on absorbent surfaces like paper, cardboard, raw wood and plasterboard. It is effective in visualizing both the fresh and old imprints. Its handling requires only a meager degree of skill. It poses no occupational hazard. Ninhydrin is a versatile reagent in the sense that its formulations are amenable to modification. Results may be improved by changing the solvent itself or by pre-treatment or post-treatment methodologies. Enhancement may also be achieved by using a suitable light source like arc lamp or like lasers. Even if this methodology fails, there is always the option of using a Ninhydrin analog as a fingerprint development reagent. It is therefore not surprising that Ninhydrin has been nicknamed as the latent fingerprint examiner's workhorse. It is also pertinent to mention that besides Ninhydrin, there are several other reagents which react with amino acids and proteins to give either colored or fluorescent products. DFO is the next in line. It is also considered to be a good reagent for developing fingerprints. But whether it is DFO or any other reagent, the results are never as good as that with Ninhydrin. No doubt, Ninhydrin takes a considerable longer time to develop fingerprints, yet cyanoacrylate also is a lengthy procedure. But then the advantage of Ninhydrin is that unlike cyanoacrylate, it is non-toxic in nature. Cyanoacrylate is highly poisonous, and while using it, great care has to be taken to avoid occupational exposure. Portable fuming chambers are required. A fan to ward off the excess vapors is also required. Such type of equipments are not required with Ninhydrin. Powder methods no doubt is more simpler to use as compared to Ninhydrin, but powder method does not give old fingerprints. Powder fixes the water content of sweat deposition. Water tends to evaporate in the course of time. In tropical countries, it takes just 24 to 48 hours for the entire water content of sweat to evaporate. On the other hand, as has been stated, Ninhydrin fixes the amino acid and protein contents. These do not vaporize as easily as water does, and so it is not surprising that prints which are many days and sometimes even months old can be developed with Ninhydrin, but these cannot be developed with powder. Fluorescent powder offers another advantage, that weak, fragmented, chance fingerprints may be developed, but then with Ninhydrin, the possibility of getting fluorescent prints is also there, although for that the post-treatment methods are required. The post-treatment is not tedious. All that is to be done is the developed fingerprint in a solution of zinc chloride and then examine it under laser. Therefore, this Ninhydrin method is one of the most trusted and one of the most favorite methods of fingerprint examiners.